This video is going to cover average stress, specifically average normal and average shear. So stress is very simply just force over an area. Depending on what type of force, depending on what type of area, depends on the type of stress that we're looking for. So for normal stress is going to be sigma, small letter sigma, and that's equal to the normal force divided by the area. Now, usually I'm not going to write it as N because that might be confused with newtons, so you're probably more likely to see it as P instead. But anyway, this is the normal force divided by the area, and the area is very specifically perpendicular to the normal force. So it is the area of the face that the normal force is sticking out of. Our second type, we have shear, and shear is tau. So it's a very curly looking T there. And it is the shear force over the area. And again, which area is that? That is the area that is parallel to the shear. So effectively, when we were drawing our normal force and our shear force off of our usual cross-sectional area, they were both talking about the same area, and that was the area of that face. But not all problems are that simple. Yes, in fact, many of them are very distinctly not that simple. So here in this picture, we have two plates, both being pulled by P. So this is an equilibrium, right? We have equal and opposite forces. Theoretically, we also have a bolt. I attempted to draw a pin, a bolt, something is being drawn there that's going through the two of these to hold the two of them together. So yes, the two plates are in equilibrium here, being pulled equally and opposite, and what's really happening as they're, quote, not moving, is we do have our stresses, and our average normal stress is equal to P over, let's call it AN for normal. Maybe we should do a capital N there. There we go. AN for normal. And that area is this face, right? Because that is the face that the force is acting on. So that's the area that's perpendicular to that. And for our shear force is V over A. But in this case, we have to ask ourselves, what is being put into shear? So shear is usually called punching shear. That's usually a nice way to think about it. Effectively, think about you punching your fist through a wall. Technically, yes, there's going to be a hole in the wall that is the size of your fist, but that's the key thing. It is the, quote, size of your fist. I think it's easier to not think of it as your fist because that's going to deal radical damage, but effectively take like a straw and try to punch it through the wall. If you do that, obviously there's going to be the hollow area where you've obviously punched the straw, but the damage is literally going to be the size of the straw, or perhaps a nail or something, right? It's not that big. And the reason is because what's causing the shear is that force that's going down across the area face there. So effectively, what we're looking at in other terms is two plates sliding in opposite directions. So I've got this plate here, and I've got this plate here, and they are sliding in opposite directions. And what that's really doing is causing a mound of problems for this little circle in the center. So the circle in the center is actually the face upon which we have our shear. So our shear value in this example that we've drawn is P, and the face that it's acting on is that little circle. So effectively, it's this little dude in here, and we'll call that AV. So in this case, our shear stress is P, again, over this time AV. Now, shear stress is the most complicated type of thing that we're going to talk about in this course, and we're going to talk about it in all sorts of different directions and things. And if you can get down shear and what shear is, then you're doing pretty good. So hopefully either watching this video a few times or doing a whole bunch of different problems to see it, hopefully it'll start to make sense. But that's the gist of it. So normal, let's think about the Oreo cookie, if you like Oreos. Normal stress is when you're pulling the two cookies straight away from each other and just leaving the gooey little middle right where it is. So you're trying to pull the cookie pieces directly apart from each other. Shear would be when you're trying to slide one cookie off the other one, just straight vertically one off the other one. And when you do the twisting action to try and get the perfect one side with cream, one side without, that twisting action is torsion. So we're talking about the two types of average stress, and that's normal and shear. So take your two cookies and either try to pull them apart or slide one off of the other. And that sliding action is the shear. So we have an example that's hopefully going to really show off this stuff. We've got a beam. AB, I mean, technically we could have little d over here. So we have ABD, the beam ABD. And he is kind of irrelevant as to what shape and size he really is. But we have a uniformly distributed load of 20 kilonewtons per meter. And we have our distances there. And we also have a rod attached to ABD, and that's rod BC, and BC is attached with a pin. So what we've got in this situation, this is like a very standard looking problem that you might see in the text, right? So this very, very generic setup. And first things first, you're probably thinking, gonna have to do some statics. And yes, we are gonna have to do some statics, but what kind of statics we do, of course, definitely depends on what we want to find. So what are we trying to find down here? We are trying to find average shear stress in the pins A and B, specifically. A, B, and C are all pins. They're all pin connected there. So we're trying to find the average shear stress in the pins A and B, and we want to find the normal stress in the rod BC. So we're going to do a little bit of both here on the same singular problem. We have some more notes here off to the side that pins A and C are in double shear, and we're going to draw a diagram of what that looks like. And they both have a diameter of 10 millimeters. It's quite small. Then we have pin B, and pin B is in single shear and has a diameter of 12 millimeters. And rod BC has a diameter of 120 millimeters. So these are all pretty small things. We, of course, have 4 meters for length, 3 meters for length, and another 4 meters for length. So first things first, we need to find forces because you can't find stress if you don't know forces. So which forces do we need? Well, technically, in order to solve for these type of things, we need the resultants at A because we want to find the shear stress at A. We also want to find the shear stress at B. So I'm going to need to know what the force is going down BC. And technically that's also going to give me the normal stress in BC as well. So I need two sets of forces here. I need the force going down BC and I need the reactions at A. So simply enough, that's going to be one free body diagram. All right, so we're going to have to zoom that out just a little bit. So we're going to draw our free body diagram for this guy. And that is a beam. And we're not going to draw it to scale because we've already seen it kind of to scale. So there we go. We have our 20 kilonewtons per meter. Technically, that's where B is. So we're going to have a force coming off of that. And that's going to be, let's look at our slope. We have 3 horizontal and 4 vertical. So this is force in member BC. And then we also have, we'll call it AY and AX. Now, hopefully you don't start off thinking AX is 0 because it's definitely not, because force BC also has a horizontal component. So we have 2 horizontals and we have 2 verticals, and we have 3 equations of equilibrium. Yes, so we're going to actually use all 3 of these. So for starters, how about we start by summing the moments about point A and set it equal to 0. That's going to take away 2 of those forces, and now we're going to be left with force BC. Which part of force BC? Just as a reminder, we can technically break force BC into 2 different directions. So force BC will have a vertical component. Force BC, this is its y component, and it will also have an x component. So an x component. So if we're going to try and find that's force BC in the x, if we're trying to take a moment about A, there is no x component for force BC because it's acting directly at A. So really, we only have the y component of force BC. So that's going to significantly reduce the amount of math that we're going to do. So about A, I'm going to start with that beautiful distributed load, and that distributed load is going to go in the negative direction for us, right? That's negative. So we have minus, and we need the force. So the force is the base. The base of this whole thing was 7 meters, see above, and the height of that rectangle is 20 kilonewtons per meter. I do always recommend that you actually write out your units so that you can watch them cancel and then realize that we're now in kilonewtons, and we also need the distance that the resultant force does make with point A. So how far away is it from the centroid over to A? That's going to be 1/2 of the 7 meters. So now we're in kilonewton meters. Great, that's a moment. Next, we also have force BC, but in the y component, and he is just in the direction of our arrows assumed. He's going down, so he's going to be creating also a negative value. So we're going to say minus, and force BC, we need the y component. Again, this is a 3, 4, 5 triangle, so if I want the y component, that's in the 4 direction, so 4/5 of force BC is going to be my y component. Again, that's force. Now I need times the distance. So the horizontal distance from force BC in the y direction over to A is 3 meters. So there we go. That's taking every single number in there, isn't it? Alrighty. So what did we discover? That force BC is not going that direction. So he's going to be negative. So we're going to get that force BC is equal to 204.17 kilonewtons. And again, it is negative, so that does mean compression. Now, in the instance that you have free body diagrams like this, I highly recommend that you don't be redrawing your arrows and you just carry that negative with you, but you have to understand that it is compression and it is going to be negative. So, there we go. So now we can actually start solving things. So let's do sum of the forces in the y direction. Cool, set it equal to 0. And what do we have? We have, starting off, we have AY. AY is going up. That's great. So AY goes up. Then we have that distributed load. And distributed load is going down. And again, the base of this dude is 7 meters. The height, 20 kilonewtons per meter. That's great, canceling down to kilonewtons. And then we have that force. Again, we just found the y component, kind of. We know that that y component, we did say he is negative. So let me show you how I'm going to do this. Currently in the direction that my arrows are drawn, because I'm not going to redraw them, he is going down. So he is going down, so minus. Again, the y component was 4/5 of FBC, but FBC, as we literally just found, see right above us, is a negative 204.17. Right, that's what we have, that's in kilonewtons. So my two negatives are going to cancel each other there, which is nice because in reality, this force is supposed to be going up, not down. So as long as you either pay attention to your arrows and your signage, everything will be okay. So what are we going to find for AY? AY is going to be 23.33 kilonewtons, and it's going up. All right, now we're going to sum the forces. We're going to sum the forces in the x direction and set it equal to 0. In the x direction, we do have AX, and we do have the horizontal component of FBC. So the horizontal component, again, in the direction that I drew it, that is the negative direction, according to my arrows. And the horizontal component is the 3/5 of FBC, but FBC we said was negative 204.17 kilonewtons. So again, my negatives are going to cancel each other here, and that's okay because again, in reality, my arrows are going the wrong direction. When you have multiple arrows drawn for a single thing and you don't want to change them, please don't. Please just carry that negative with you. All will be okay. So we actually find that AX is going the opposite direction. AX is going to be 122.5 kilonewtons, but he's going that way. So again, always keep your value, your unit, and your arrows with you at all times, your directions with you so that you don't get them confused. So cool, we found that, right? Let's go through and update our values just to make our little free body diagram a little bit easier. So our AX, let's do it in, I guess, red pen over here. We're going to cross these out. AY, he's 23.33, and he is going up. AX, we're going to say he's negative, so we know the direction's wrong there, 122.5. And FBC, again, FBC, we're going to cross him out, and he is negative 204.17. Okay, so when you are going through, don't necessarily change the arrows, just keep your plus and minus with you and all will be okay. So now we found our forces. That's step 1, because you can't find stress if you don't have a force. So now we need to know about what areas and what we're doing with said areas. So the first part was to find average shear stress in the pins. Yes, in the pins, not the beam. Nobody cares about the beam. We care about actually the pins. So fun little thing about our pins, right? Pins A and C. Well, we're looking at two different ones. We want A and then we want B. So we're going to have to do two separate things here. A and C are in double shear. Double shear. What does that mean? Double shear means that when you're looking at this beam, let's say that's the cross section of my beam here. And there's obviously a pin going through it. It's pin connected, right? So there's my pin. And that pin, of course, has a diameter of 10. He's going to be a little bit longer than that, though. Let's make him long. There we go. So there's my really terribly drawn diameter 10 pin here. And he is still not long enough. There we go. In order to have this block connected to things, he has to be connected to, effectively, to other blocks that are standing. So there we go. We effectively have a fixed end that this normally we would draw it like a little triangle, right? There's our triangle with our thing. Yeah, really what this triangle looks like in reality is this. Yep, we have two blocks holding in the middle beam. So we're holding in this middle beam piece. Maybe it looks better if it's a bit bigger. So this is our beam. And the rest of these, all of this stuff here and here, these two blocks and the pin are actually what that triangle looks like in reality. So this pin's going through the beam, and the beam, it does get to rotate, right? It's just kind of freely being, suspended, so it can rotate, but it cannot move in the X nor in the Y directions because that pin's locking it in place. So again, what we said was this has a diameter of 10 millimeters. So our AY force and our AX force are acting. This one's kind of difficult to draw. We have the Y direction force, and the X direction force is like going into the page, coming out of the page, however you want to look at it. So effectively, what we're going to do, if I want to find the actual shear in this pin, is I have to take the resultant of my reaction at A. So at A, we had a box, right? Here's our beam, blown up nice and big. We're going to have, it's technically going out and it's technically going up. So in total, what it's going to look like is holding this direction. So it's pulling that direction, that is the reaction at A, off at, it should actually be the other direction, it should be going up. It's that way. So there's the reaction at A. It's holding it up and over, it's keeping it from flying away on us. And all of that force is acting along where? We're taking this beam and we're trying to remove it from these two spots, right? Those two spots are holding it in place. So as we're yanking this, what's going to happen to that rod? It's going to snap at those locations. That is actually what's going to happen. So when we have our average shear, which again is supposed to be V over A, the average shear that we have is the resultant force at A over what area? Now, of course, because this is in double shear, we do have 2 shear planes. So that's going to be 2 times the area. And what is the area? We'll do it in purple. If this is a diameter 10, remember that the area of a rod is pi over 4d squared. Okay, because you know that for a circle it's pi r squared. R divided by 2 is the diameter, so square the divided by 2 part, you get divided by 4, right? That's just basic manipulation of equations. So here we're going to have our area. If we plug in 10 and square it, let's not actually solve for that. We're going to plug it in down here. We're just going to plug in all the numbers. How about that? So we've got average shear stress. This is in pin A, right? The double shear one. This was pin A. This is double shear. So the average one, we said reaction of A, or the resultant of A. So the resultant of A, this is statics, right? If you have 2 forces and you want to create the resultant, I mean, literally that's the opposite of what we did with force BC. We had an X and a Y component, and now we're going to smash them together to get the resultant. So that's just triangle math. That's just triangle math. So he's going to be the square root, because you know, get the hypotenuse, it's a squared plus b squared equals c squared. So the square root of the y component, which is 23.33 squared, plus the x component, which is 122.5 squared. Now you might be saying, oh, one of them's negative. When you square the negative, it goes away. Yes, it's okay. That can just go away. Divided by the area, which we said was pi over 4 times 10 millimeters squared. But also times 2, because there are 2 shear planes. So what do we get in total? Again, making sure that you're keeping up with your units. Again, these forces were in kilonewtons. This is going to be in millimeters squared. So therefore, we're going to get 0.794, and kilonewtons per millimeter squared is a gigapascal, but who talks about decimal values of gigapascals? If you don't even have 1 gigapascal, that's kind of ridiculous. So instead, we're going to drop down by 3, and we're going to call this 794 megapascals. Just do a little itty bitty little unit conversion, move the decimal over 3 times, and call it a great day. So that's for A. Now let's look at pin B. Pin B, according to our thing, pin B is in single shear. Has a bigger diameter, right? Single shear. So what single shear is going to look like is, let's say we have the beam, and there is, let's just pretend it's another beam here. And we have a pin that goes through. So this is what pin B looks like. It is quite simply just this pin right here. It's two things held together by effectively one little bolt. And they can freely rotate, right? They can freely rotate. So that's in single shear. This is our single shear, only one shear plane, and the only shear plane is right here. So again, that diameter, we said the diameter here was 12 millimeters for pin B. So this time, if I want to find the shear force, the average shear force at B, let's remind ourselves where B actually is. This is B. So we can't use the same forces that we did for A, because very clearly that's not happening at B. That was happening at A. So what's happening at B? That's force BC. Force BC is happening at B. So we're going to use him in our little equation here. So force BC, we said, was 204.17 kilonewtons divided by, there's only one shear plane, so this is single shear, divided by the area of that pin B. So that's just going to be pi divided by 4 times the diameter, which is 12 millimeters squared. So again, kilonewtons per millimeter squared is going to give us gigapascals, and we're going to get 1.80 gigapascals. Okay, so single shear much easier than double shear. Again, that's just the direction of the force going there. Now we want to find the average normal stress in BC. And finally, that's where we're going to utilize the diameter for BC. Up until this point, we've been talking about the pins. We're talking about the shear stress that are in the pins. And again, remember that the thing that was in actual shear stress at the very beginning of this video was not the plates. The thing that was in shear stress were the pins holding it together. So usually when we're talking shear, we're really not talking along the face of the object. Usually, sometimes we are. But in the case that we have connections, shear in the pins is talking about the connecting pieces themselves. So just pay attention to that. So last but not least, the average normal stress in BC is perhaps the easiest thing, hence why we saved them for the very end. So again, average normal stress for BC is simply the axial force, whatever that is. Maybe let's not call it P, let's call it what it actually is. The axial force of BC is force BC over the area of rod BC. Key is, again, the easiest thing to solve for. So we said that that force is minus 204.17 kilonewtons over the area of BC, and it is again a rod, so that's pi over 4 times dd, though, 120 millimeters squared. So our average normal stress for BC is equal to, it would technically be 0.0181 gigapascals. But that's really weird to talk about, so we're going to say that the average in BC is actually equal to 18.1 megapascals. Now it is negative, which does mean in compression. So there we go. Now you might be wondering, why the negative here and not the negative here? Because normal has a direction. Normal has either a tension or a compression direction. Shear does not have a direction because in one face it's going down and in the other face it's going up. So it doesn't have a direction, it has a magnitude. Whereas normal very specifically is either in compression or in tension. So I hope that clears that confusion up if there was any. So hopefully through this, you're feeling pretty confident. The only problem that you'll run into with shear stress is, again, it's not actually the complication of the equation, because the equation's rather simple. It's trying to figure out what is the area that's actually in shear. Where is the sliding happening and what is resisting said sliding? And that's the face of the shear. If you can get that, then this isn't too terrible.